Assalamu alaikum warahmatullahi wabarakatuh.
Welcome to a deep dive. Today we're lifting the hood on something that is, well, both a precise science and, you could say, a delicate art form. It's absolutely fundamental to performance in the race car setup. We've pulled together quite a stack of sources here. Everything's from really in-depth tuning guides, crash courses on vehicle dynamics, even some insider glimpses into how the professional race teams tackle this whole challenge.
That's right. And our mission for this deep dive is basically to peel back the layers on the systematic process teams use to optimize a car's performance. We want to dig into the core principles of vehicle dynamics, what dictates how a car behaves, and see how every single adjustment, from something as basic as tire pressures to really complex aero tweaks, how it all connects.
Think of this as your shortcut, maybe, to understanding why race cars are such incredibly complex machines, and why engineers, drivers, they spend just endless hours finessing every little detail. Okay, let's unpack this.
So, at its heart, vehicle dynamics is really the study of how a car moves and responds to, well, everything acting upon it: driver inputs, the road surface, the forces of physics. It's the absolute foundation for understanding performance at the limit.
Okay, so it's essentially applying physics to a car going really, really fast.
Yeah.
And what's the ultimate goal in racing from this dynamics perspective?
The primary goal always is to maximize the car's ability to generate force. In all directions, so longitudinal for accelerating and braking and lateral for cornering. And critically, you do that by optimizing the interaction between the tires and the track surface.
Right, and this is where our sources really, really emphasize something fundamental. The tire is king. Everything else is just there to support the tire.
Precisely. Yeah, the tire is the single point of contact. It's like the handshake between the car and the road. The entire vehicle's design, its setup, it's all dedicated to creating the perfect environment for those 4 patches of rubber to generate maximum grip. So understanding how factors like slick angle, temperature, pressure, and load sensitivity affect that contact is absolutely paramount.
Okay, hold on a sec. Slip angle. Load sensitivity. For listeners who maybe don't live and breathe race engineering, what exactly do those terms mean here?
Ah, good point. Okay, so think of slip angle as the difference between the direction a tire is pointed and the direction it's actually traveling. Sounds weird, but a tire needs a small slip angle to generate cornering force. It's not just rolling purely sideways. That slight angle, that slip, is what generates the grip. And load sensitivity, well, that refers to the fact that tires don't generate grip linearly with the vertical load you put on them. If you double the load on a tire, you get more grip, sure, but you don't actually get double the grip. Yeah, this non-linearity is hugely important because it means you really want to spread the load across the tires as effectively as possible.
Ah, okay. So setup isn't just about making the car feel responsive. It's really about manipulating weight and forces to keep those tires in their, happy place, generating maximum grip.
Exactly. Setup is how you tune the car's behavior. It's handling balance, overall grip levels, stability, even durability to the specific requirements of a track, the current conditions, and yeah, even the driver's style. Doing this effectively unlocks performance. It irons out handling quirks like understeer or oversteer, and ultimately leads to faster, more consistent lap times.
Okay, with a machine this complex, so many variables, where do you even begin? Tuning must feel, overwhelming without a clear process.
Oh, it absolutely would be. That's why a structured, systematic approach is universally recommended. Doesn't matter if you're tuning a multi-million-dollar race car or just tweaking settings in a sim racer. It allows you to tackle one area at a time, understand its impact, and build a stable baseline without, chasing your tail.
Right. Let's walk through that recommended sequence our sources highlight. What's the absolute starting point? Step 1.
You always start with the tires themselves. Tire pressures and temperatures. Setting the correct cold pressures is the first step. That's what ensures the tires reach and maintain their optimal operating temperature range when you're running, which is, crucial for maximum grip and even wear. It establishes the most fundamental part of that contact patch.
Makes perfect sense. Get the primary interface right first. Okay, once pressures are sort of dialed in, what's the next logical step?
Then you address alignment, specifically camber, toe, and caster. These angles determine how the wheels sit relative to the car and the road. So camber is the inward or outward tilt of the wheel when you look at it from the front. You set it to maximize the tire's contact patch under cornering loads, when the suspension is compressed and the car is rolling. Toe is the angle of the wheels relative to the car's center line when viewed from above. It affects straight line stability and how the car initially responds when you turn the wheel. Proper alignment ensures the tire is working effectively both street and cornering.
And the sources mentioned needing to recheck tire temps after you make alignment changes. Why is that?
Yes, exactly, because any suspension tweaks you make to adjust camber or toe directly affect how the tire contacts the road and how load is distributed across it. And that, in turn, affects how the tire heats up. It's all part of that iterative nature. Changes in one area definitely influence others.
Okay, so tires first, then how they sit on the road. As you start building speed, what external factor starts to play a really huge role?
That would be aerodynamics. This involves setting wing angles, ride height, and potentially something called rake. Downforce, right, generated by wings and the car's shape basically presses the car into the track. That increases the vertical load on the tires and therefore increases potential cornering grip. But there's always a but. It comes at the cost of drag, which slows you down on the straights. So you're balancing front and rear wing angles for the desired downforce level and the aero balance. More downforce for twisty tracks needing grip, less for high-speed tracks where top speed is king.
And rake, we saw that mentioned. What's that about?
Rake is simply when the rear ride height is set higher than the front. So the car has this sort of wedge shape. This angle significantly impacts how air flows under the car, which is critical for generating underbody downforce, sometimes called ground effect. Lowering the car overall generally increases ground effect, but then you carry the risk of bottoming out on bumps or curbs. Again, changing ride height or rake impacts suspension geometry and how load gets to the tires, which, yeah, could mean you need to revisit earlier steps like alignment or temps.
Wow, it really highlights how everything is so interconnected. Okay, after tuning the air flowing around the car, where do we go next in this sequence?
Then you move to the core mechanical system that manages load transfer, the suspension. This includes the springs and the anti-roll bars. The goal here is really to balance responsiveness and stability. Springs support the car's weight and absorb bumps. Now, softer springs generally allow the tire to stay in contact with uneven surfaces better, potentially increasing mechanical grip, right?
Right.
But they can also lead to excessive body roll and maybe less responsive handling. Stiffer springs reduce body motion, giving you sharper turn-in and feel, but they can cause the tires to sort of skip over bumps, reducing grip if they lose contact.
And how do the anti-roll bars fit in with the springs? What's their specific job?
Anti-roll bars, ARBs, sometimes called sway bars. They connect opposite wheels and basically resist body roll in corners. They're a crucial tool for tuning handling balance, that understeer-oversteer characteristic. So a stiffer front ARB reduces front body roll, keeps the front suspension flatter. This shifts more load onto the outer front tire relative to the inner one. But compared to the rear, the front end might reach its grip limit sooner under cornering load. Result, more understeer. Conversely, a stiffer rear ARB reduces rear roll, potentially leading to more oversteer. So adjusting the balance of stiffness between the front and rear ARBs is a primary method for fine-tuning that balance.
Okay, so springs determine how much the suspension moves, roughly, and ARBs control how much it rolls sideways. What about the speed of that movement?
That's where the dampers come in, often called shocks or shock absorbers. Dampers control the rate at which the suspension compresses, that's the bumper compression setting, and extends, which is rebound or extension. Optimizing these settings fine-tunes how the car behaves over curbs, through bumps, and critically during weight transfer events like braking and acceleration. Softer damping generally increases compliance and grip on rough surfaces, but can make the car feel a bit floaty or uncontrolled. Stiffer damping sharpens response, but risks upsetting the car or causing tires to lose contact on sharp bumps. And the sources note you often tune high-speed damping for quick, sudden inputs, like hitting a curb hard, and low-speed damping for slower, more gradual inputs, like body roll in a long corner or weight transfer under braking.
Okay, we've covered the tires, how they sit, how air affects the car, the main suspension bits, and how they move. Now, what about getting the power down and slowing the car down?
Right. That brings us neatly to the differential and drivetrain, followed by the brakes. The differential manages how engine torque is distributed between the driven wheels. This has a huge impact on traction out of corners and stability on entry. Gear ratios are adjusted for the best acceleration and top speed balance for a specific track layout. And for brakes, you tune brake bias. That's the front-to-rear distribution of braking force and pressure settings for stable deceleration and to prevent wheel lockups. You tailor it to the track's braking zones and, of course, your driving technique.
How exactly does the differential impact entry versus exit? You mentioned that distinction.
Yeah, so think about a more locked differential. It limits the difference in speed between the left and right wheels. On corner exit, under power, this helps prevent the inner wheel from just spinning uselessly, which would happen with a very open diff, so it improves traction, gets the power down. However, on corner entry off power, If the diff is very locked, it can resist the wheels turning at different speeds, which is needed for rotation. This can potentially induce understeer, make the car want to push straight. So you often tune power lock specifically for that exit traction, and coast lock how the diff behaves off throttle for stability on corner entry.
Okay, fascinating. So after going through all these intricate steps, tires, alignment, aero, suspension, dampers, diff, brakes, is there a final check? Are you done?
Never quite done. You always finish with a final tire check. You have to revisit pressures and temperatures because every single change you made, alignment, aero, suspension, has likely altered how load is distributed to the tires and therefore how they are heating up. You absolutely need to ensure they are still running within their optimal temperature and pressure window. It brings it all back to the tires.
That sequential process is really illuminating. It makes sense of a complex task. Maybe let's revisit a few of those key areas we touched on in the sequence and dig just a bit deeper into how those adjustments actually achieve their effects, drawing from what our sources say.
Good idea. The suspension settings, like we mentioned, are really fascinating because they directly manage that critical interplay between maintaining tire contact for grip and controlling body motion for responsiveness and stability. It's a real balancing act.
Right, so going back to spring rates, how does that trade-off, softer for grips, different for response, how does it actually work mechanically?
Well, it really comes down to how the spring allows the tire to follow the road surface. A softer spring compresses more easily, right? So it allows the wheel to move up and down over undulations and bumps, keeping the tire pressed into the surface. This is vital for mechanical grip, especially on bumpy tracks. But that compliance means more body roll, more pitch, which can feel imprecise and maybe delay weight transfer, reducing responsiveness. A stiffer spring resists this movement more, keeps the car flatter, feels more direct. But if it's too stiff, the tire can literally bounce over bumps instead of absorbing them. That leads to moments of reduced or lost contact, and boom, less grip.
And the anti-roll bars. You mentioned they influence understeer, oversteer. Can you elaborate a bit more on the mechanism there? How does stiffening a bar cause, say, understeer?
Yeah, think about a car cornering hard. Weight transfers to the outside wheels, causing body roll. The ARB resists this roll. Now, by making the front ARB stiffer, you reduce front body roll. Okay. But this resistance also means the outer front tire takes on a disproportionately larger share of the lateral load compared to the inner front tire. And because of the tire's load sensitivity, remember, less than double the grip for double the load.
Ah, right.
That concentration of load on the outer tire actually reduces the total grip available from the front axle compared to if the load was more evenly shared with, say, a bit more body roll. So if the front axle hits its now reduced grip limit before the rear axle does, you get understeer. Stiffening the rear ARB has the opposite effect. It shifts the balance, potentially pushing the car towards oversteer. It's all about how the bar changes the distribution of load across the axle during roll.
That makes a lot more sense. It's not just resisting roll, it's changing the load distribution.
Yeah.
Okay, how about dampers? Again, the bump and rebound settings. How does controlling the speed of movement make such a difference?
Controlling the speed is all about preventing unwanted oscillations or sudden load changes that can upset the car. For example, when you brake really heavily, weight pitches forward. Rebound damping on the rear shocks and bump damping on the front. Shocks control how quickly that weight transfer happens and how quickly the suspension settles afterwards. Too soft, and the car might bounce or oscillate after braking. Too stiff, and the suspension might pack down or feel harsh, upsetting the tires. Similarly, when hitting a curb, the high-speed bump damping controls the initial shock absorption, while the high-speed rebound controls how quickly the wheel drops back down to maintain contact with the road surface on the other side of the curb. It's fundamentally about maintaining control and tire contact through all these transient events.
Got it. Now, aerodynamics seems like a slightly different beast, dealing with air pressure rather than mechanical links. How do those wing angles and ride heights translate directly into handling changes on track?
They directly add vertical load to the tires, essentially increasing their grip potential, but primarily at speed. A higher rear wing angle creates more downforce at the back, increasing rear grip and reducing oversteer tendencies. But it adds drag, slowing you down on the straights. A higher front wing angle, or maybe a lower front ride height, especially if you're running rake, adds front downforce. That increases front grip for better turn-in and reduces understeer. But again, adds drag, and you have the risk of hitting the ground, bottoming out. So it's this constant trade-off between straight line speed and cornering capability. And also, crucially, the balance between front and rear downforce, which profoundly impacts the car's high-speed handling characteristics.
And the differential, You explained power and coast lock earlier.
Yeah.
But how does that torque distribution physically change the car's behavior? Like what's happening at the wheels?
Okay, imagine exiting a corner with a very open diff.
Okay.
The inner wheel has less load on it, right? So it takes the path of least resistance and just spins up, wasting engine power. A locked diff forces that power to go to the outer wheel too, which has more load and can actually use the power to accelerate the car forward. Much better traction. But on entry, if you're off throttle and the diff is locked, the inside wheel wants to turn slower than the outside wheel as you turn the steering wheel. The locked diff resists this speed difference, effectively pushing the car straight on, hindering its willingness to rotate, potentially causing understeer. So tuning the diff is all about finding that sweet spot between maximum exit traction and sufficient entry rotation and stability.
Makes sense. Lastly, brake bias. Why is shifting the braking force front to rear so impactful? Seems subtle, but clearly isn't.
It's all about managing where the grip limit is reached first under braking. When you brake hard, weight shifts forward, putting much more load on the front tires. Now, if you send too much braking force to the rear, too much rear bias, those less loaded rear tires will lock up really easily. That destabilizes the car, can cause it to spin, very bad. More front bias uses the heavily loaded front tires more effectively. This increases stability under braking because the front axle has more available grip for deceleration. But push it too far forward and the front tires lock up first, which results in understeer while you're braking, meaning you can't turn. So it's adjusted to use the available grip most effectively under braking, preventing lockups while maintaining stability. Or sometimes drivers use a slight rear bias intentionally to help rotate the car on corner entry, depending on their preference in the corner itself.
It's really clear this isn't a static process at all. You said it, but then things change. The sources also talk quite a bit about how track conditions play a massive role. Does that completely change the setup approach or the sequence?
Oh, absolutely. Track conditions like the current grip level, is it wet or dry? The temperature, how the surface evolves over a race weekend, they significantly dictate your setup priorities and choices. For instance, in really low grip conditions, like a wet track, the absolute priority shifts heavily towards maximizing mechanical grip and stability. Why? Because aerodynamic downforce is much less effective at lower speeds.
So in the wet, you'd probably lean toward softer settings generally, more compliance.
Precisely. You'd focus intensely on tire pressures and camber first, probably running higher pressures initially to generate heat, maybe more negative camber for bite. Then you'd likely soften the springs and dampers quite a bit to help the tire follow the slippery surface and maintain contact. You'd also just brake bias heavily forward to prevent those dreaded rear lockups. And initially, aerodynamic settings become less critical due to the lower overall speeds. Then, as the track maybe dries out and starts to rubber in, you might gradually stiffen the suspension back up, maybe lower the ride height slightly, add more aerodynamic downforce to exploit the improving grip and the increasing speeds.
It really sounds like setup is just this constant dance with the environment, doesn't it? Not a fixed endpoint you reach.
Exactly right. It's an iterative process. You're constantly adapting to the track and the conditions as they change, always trying to keep the tires in their optimal window and the car balanced underneath the driver.
The sources also mentioned mass distribution. How does the physical weight of the car and where it sits fit into all these dynamic adjustments we've been talking about?
Mass distribution, which includes the overall weight distribution front to rear, side to side, and crucially, the position of the center of gravity, the cog, is absolutely fundamental. It dictates how weight transfers under acceleration, braking, and cornering. A lower cog, for example, means less weight transfer for a given cornering force, less body roll, less pitch. That inherently increases stability and changes how the tires are loaded during those transient moments.
And the front to rear weight split, that affects things like understeer or oversteer directly.
It certainly does, although it's often something you manage through careful corner weighting and balancing the suspension setup around the inherent weight distribution of the chassis. A car with, say, a more rearward weight bias might naturally have more traction for rear-wheel drive acceleration, but could be inherently more prone to oversteer. Conversely, a more forward bias tends to increase stability under braking and on corner entry, but might lead to more understeer. This is why professional teams spend considerable time using corner weight scales. These are precise scales placed under each wheel to ensure the static weight is perfectly balanced across the four corners. It's a critical starting point for a predictable handling car.
This level of detail really makes you wonder about the difference between, say, someone tuning their car for a track day or maybe in a simulator versus a professional race team. What separates their approaches? The fundamentals seem similar, but the execution must be different.
Oh, the scale and sophistication are vastly different. Professional teams do the overwhelming majority. Some sources suggest as much as 90% of their setup development work away from the track, using highly advanced simulations. They build incredibly complex physics-based models of the car, the tires, the track itself, running thousands upon thousands of virtual kilometers to arrive at a near-optimal baseline setup before the car even leaves the factory transporter.
Wow, 90% in simulation. That's incredible. What are the biggest advantages and maybe some limitations of relying so heavily on virtual testing?
Well, the advantage is pretty obvious. You get essentially infinite testing time, perfect repeatability, and the ability to isolate variables in a way you just can't in the real world. You can explore corners of the setup matrix you simply wouldn't have time for during a busy track weekend. The limitation, though, is that the simulation is only ever as good as the data and the models you feed into it. It can't perfectly replicate every single nuance of real-world tire behavior, especially wear and degradation, or track surface inconsistencies, microclimates, things like that.
So track time becomes more about validating the sim work and then fine-tuning based on reality.
Exactly. Trackside time is incredibly precious, often constrained by regulations like parc fermé rules or just limited practice sessions. Teams make very targeted, data-driven adjustments based on driver feedback and real-time telemetry. But they're refining a strong foundation that was built virtually. They're generally not starting from scratch at the circuit.
Speaking of data and refinement, what are the essential tools for anyone serious about car setup, whether you're a pro or just an enthusiast trying to get faster?
You absolutely need tools for precise measurement. For the chassis and suspension, you need corner weight scales to check that weight distribution. You need accurate toe, camber, and caster gauges for alignment adjustments. And ride height gauges. Precision is key. For tires, a really precise tire pressure gauge is non-negotiable, and a pyrometer is vital. That's what measures the tire's surface temperature across the tread, inner, middle, and outer sections immediately after a run. Those temperature spreads tell you a lot about whether your alignment settings, like camber, are working effectively under load.
And the data acquisition side of things. Telemetry.
Oh, indispensable now, even at enthusiast levels. Telemetry systems log all sorts of data: suspension travel, steering angle, throttle and brake application, G-forces, increasingly sophisticated tire temperature monitoring, too. Lap timing and sector analysis let you correlate changes directly with performance improvements or losses in specific parts of the track. And, perhaps most crucially, overlaying driver feedback onto all that objective data. How the car feels is subjective, yes, but it's essential for understanding why the data looks the way it does.
So you've made changes, used the tools, looked at the data. How do you definitively know if a setup change was actually successful? Is it just about finding that magic lap time number?
Lap time improvement, especially a consistent reduction over multiple laps, is certainly the most direct measure, yeah? But true success is really a blend of that objective data and the subjective driver feedback. Beyond just raw pace, you look at consistency. Are the lap times tighter together? Does the car feel more predictable lap after lap? Then you dive into the telemetry data. Did the change result in smoother steering inputs, less tire slip showing up, higher minimum corner speeds? More effective braking, perhaps. These are objective signs the car is working better with the driver.
And what the driver feels is genuinely weighted equally with the stopwatch.
Absolutely crucial. I mean, if the driver reports the car feels more balanced, more predictable, confidence-inspiring, or just easier to drive consistently at the limit, that's a huge sign of success. Even if the single fastest lap time wasn't some massive leap forward, ultimately the best setup is one that allows the driver to extract the car's potential lap after lap without constantly fighting it.
It's just amazing how much science, engineering, data, and that crucial driver feel are all involved. But even at the absolute pinnacle of the sport, with all this incredible technology and simulation power, do the sources indicate there are still fundamental aspects of setup or vehicle dynamics that are just really hard to fully measure, model, or understand? Are there remaining blind spots?
Yes, according to recent research and a lot of discussion in the professional world, there definitely are. A significant blind spot is the accurate measurement, and especially the predictive modeling, of internal tire temperature. Surface temperature pyrometers give you a snapshot, sure, but the temperature inside the tire structure, within the carcass and the air volume, is what fundamentally dictates its pressure buildup and its grip characteristics over a long run. And it's incredibly difficult to measure accurately in real time, and even harder to model perfectly across different tire compounds and track conditions.
Oh, Interesting. What else?
Another challenge mentioned is the real-time adaptability of these increasingly sophisticated AI-based race strategy tools. While they're great in simulation, bridging the gap to making optimal split-second strategic decisions in the messy, dynamic environment of a live race, reacting perfectly to unpredictable events like safety cars or sudden rain, that remains an ongoing frontier. How do you make the AI truly robust to the unexpected? And finally, there's a more subtle but maybe important gap in fully correlating fine-grained driver inputs, the tiny steering adjustments, micro corrections, or the specific line choices through a corner with their precise real-time impact on tire thermal dynamics and wear. How exactly does that tiny steering adjustment change the temperature profile across the tire face over the next few seconds or laps? That incredibly detailed level of interaction isn't yet fully understood or modeled comprehensively.
Wow, this deep dive has really opened up the sheer complexity and fascination of race car setup science. We've seen how it's deeply rooted in fundamental vehicle dynamics, why the tire is absolutely paramount, walked through that systematic process from pressures to aero, and even got a glimpse into the high-tech world of professional simulation and the tools of the trade.
It absolutely underscores the iterative nature of the whole process, doesn't it? And how every single component is part of this deeply interconnected system. It requires data, precision tools, and that critical driver feedback to optimize for any specific challenge track car conditions.
And I find it utterly fascinating that even at the highest levels, with all the data, all the simulation power imaginable, there are still these fundamental areas like fully understanding what's truly happening inside that critical tire, or that subtle, intricate dance between driver input and tire response that remain elusive puzzles.
So thinking about those blind spots you mentioned, that lack of perfect understanding, even in this focused domain, it does make you pause and consider, right? If achieving perfect, real-time understanding and control of something as seemingly contained and critical as a race tire's temperature profile is still an unsolved problem, despite decades of effort and immense resources, well, what does that imply about the ultimate limits of our ability to perfectly model and control other, perhaps even more complex dynamic systems in the world around us?
That is definitely something to chew on. We hope you enjoyed this deep dive into the science and art of race car setup.
Why did the race car driver bring string to the track? Because he wanted to tie his lap time. Alright, speed demons, that wraps up this episode of the Overflow podcast, your pit stop for everything fast, furious, and just a little bit nerdy. Today we dug deep into the art of professional racing car setup, from camber angles to why your spoiler isn't just for show-offs in parking lots. If your car isn't going faster after this episode, well, it might be your driving. Don't forget to like, comment, share, and subscribe. It keeps our engine running and helps us stay ahead of the algorithm faster than a Formula One pit crew. Catch you in the next lap. And remember, if you're not first, you're probably listening to the wrong podcast. This is the Overflow podcast. Signing off with tire smoke and bad puns.